Perfect. Everything is looks perfect. Thank you for the organizer to give me the opportunity to talk to this community. So the organizer asked me to speak about the image reconstruction and AI. But my background is more on microscopy engineering or apply math that I apply to bioimaging. So I will focus on the microscopy aspect, but I hope that it's okay for also it's useful for you in marine biology. So the image restoration is a very broad topic. I cannot cover everything, but I will present the most common operation in microscopy, which is denoising and deconvolution. And at the end, I would like also to focus and to discuss about the two paradigms that we are facing now, which is the physics-driven method and the data-driven method that Tali just speak also a little bit at the end. And effectively, at the emergence of the AI is starting to completely redraw some aspect of our fields and the way that we are designing the image restoration. So before to speak about the image restoration, I would like to focus on the image acquisition and to think what we do in image acquisition. So when we have an object, we use an imaging system, let's say a lens, that to provide an image, and then we have a detection systems. Let's say it could be a camera to obtain data or digital images. And the question is, how do the image reach your eyes or the screens? And so there is all these systems. I should mention, and it's very important also in marine, the illumination systems. Usually you illuminate the object. We use more light in light microscopy, obviously. But all these systems affect the quality of the image, and there is obviously unavoidable degradation, and that I want to show the kind of degradation that we have in microscopy. So we have the one that coming from the illumination systems. So typically the non-uniform background, uneven illumination, some other artifact with the scattering and so on. We have also the one that comes from the imaging system itself, so typically the diffraction limited due to the light and the kind of noise that we can have in microscopy. So in microscopy, we are really pushing the instrument at the limit. And we have always to deal with this pyramid of frustration and that we have. We have to find a good trade-off between the spatial resolution, temporal resolution, contrast, and also to protect the specimen due to the phototoxicity of the light. That's not the only thing that we have. We work here. I'm focused specifically on the multidimensional fluorescent microscopy, and that means we have degradation in 2D, but we have degradation due to the fact that we acquire image in n dimension. We speak very often about 5D. 2D is the lateral plane, but we have also the 3D with typically the out of focus, the problem of resolution in the Z steps. We acquire images in time-lapse microscopy, so that's also introduced some other kind of degradation. And due to the fact that we illuminate our sample in different wavelengths, there is also some other artifact that could happen. So that's all the kind of image degradation that we can have. So I like also to speak about to see the scene as an integrative system in imaging. So we have, in one side, we have the instrument. So typically we acquire an image, we have an object, we acquire an image through a physical image formation. So it's in real life, it's physics. And here, after the image comes to the computer and we start to make digital image restoration. So the goal of the image restoration, in fact, there is two goals in the image restoration. We want to have better images for human observation, and that's typically what Tali tried to do, to have a proof of existence of something, to generate good illustration for a paper. That's a qualitative image restoration. But we have in the other side quantitative image restoration. The goal here is to provide an image that we can use in a computer to make some other measurement, typically segmentation, measure the gene expression, or measure some speed of protein and so on. So always we have to keep in mind that we have the two goals, and obviously the one which is interesting in microscopy on many fields is to starting to use the image to make measurements. And we should never forget that if we are this motto, which is garbage in, garbage out. So if we have bad image here, we cannot expect to restore, to have a very good image after image restoration. Obviously, it's linked to the fact that the acquisition is good or bad. So now if I enter into more in depth in the image formation model. So here, what we consider as a model in microscopy is the following things. So it's a much more simplified than the model that Talish just shown before. But that's the common things that we have in microscopy. So we have our object going to the microscopes, and we summarize all the information, the deformation, in what we call a point spread function. Here it's I use the matrix representation, and I call edge. It is a PSF, this point spread function. And in addition, we have the noise on the top, the noise of the detector. So if I consider this very simple model, it's still very useful for many kind of problems. In fact, in bio, also in medical imaging, typically the denoising problem is just the fact that edge is an identity. So we have just the noise on the top of the image. The deconvolution, we consider the edge exactly as the PSF, but there is other modality, typically structural elimination microscopy, where the edge in that time is a convolution followed by a modulation with interference. We have also the optical projection tomography that can be summarized in this edge. So in that case, it's an integration or projection, and then we have a different rotation. So all these operators are linear operator, and it's possible to put all these operators in the edge. Okay, so that's the image formation model that we consider. So now if we want to make the image restoration, so what we have to do is to solve this equation. So we want to recover an estimation of x tilde, using the measurement y that we have here. So x is my object, y is my measurements, so obtained by the image formation model, and I want to recover x tilde. So there is different way to approach these things. In the past, people use what we call rule-based method now. So we try to design let's say, a filter. So we can consider that edge is very often in microscopy, it's a low-pass filter. So we have to design what we say it could be a high-pass filter, such a way that we cancel the effect of the edge. But using a high-pass filter on the noise is not a very good idea, because obviously you increase the noise in the image. So very often that kind of method do not work very well. So people have tried to develop other approach. So the first one is the physics-driven method. In that case, we try to minimize a cost function, a quantity here. Usually we have two terms. So the term which is attached to the data term that we try to minimize. And we add on the top a regularization. So in the regularization, you can add some prior on the solution that you have. And you can balance the two terms with a hyperparameter lambda. So that's the physics-driven method. And now with the powerful computer that we have, we can try to train a neural network, so using a lot of data. So it's data-driven method. So in that case, we learn the function that map y to x tilde, and what we have to learn is million of parameters of the neural network, which is included in that function. So this problem is of restoration is a very ill-posed problem. And so because of first, the solution is not unique. We have a number of unknowns, which is largely greater than the number of measurements. So it's, if we return back to the school, your teacher will say that it's impossible to solve, so that we have to deal with. Also, very often the data is very degraded. We have only partial data. We have the noise, and the other things that's very important for the physics-driven method, because in the physics-driven method we rely a lot on the knowledge of age, and obviously we never know very exactly the age function on the PSF. So now in bioimaging, there is this huge movement through deep learning method. And probably each month you have a new paper with new function, new models, new neural network, new way to train data. So it's happened in the image reconstruction. Image reconstruction, that means we the input is some measurement, and we want to reconstruct an image. And typically that's a localization microscopy, structural elimination microscopy, or computed tomography. It happens also, we use deep learning, in fact, in image restoration. I will talk about the denoising, deconvolution, but it's also registration, interpolation, correction on the drift, and many other things. But the huge movement is in that place, so image analysis. So where, because it's linked to the computer vision, where we want to probably make image classification or image segmentation. I should say that 90% of the paper on deep learning happened in that field, in the image analysis, because that works pretty well. We can rely on the data itself. Okay, so here I have there is a new paper now, that present all the place where we can use deep learning in microscopy. You see that there is many places, including artificial labeling, or improving the temporal resolution, improving the spatial resolution, correction of the drift, and so on. Obviously, there is also segmentation and tracking. And the nice thing is also because now we can, with deep learning, we can process an image rapidly. We can also, during the acquisition, modify the parameter of the acquisition such a way based on the result of the output of a deep learning system. So it's what we call the smart microscopy. So now we will focus on denoising and deconvolution. Just so there is some aircraft. Sorry. Okay. That's okay? Yeah, okay. Sorry. Denoising first. Okay, no, sorry. I will also mention the kind of learning strategy that we have. So here I will speak mostly about the supervised learning. So in that case, there is two kinds of supervised learning. The output could be a pixel classification or could be a pixel regression. Pixel classification is used for segmentation, and regression is used for image restoration. So when we have a supervised system, obviously the question that we have to deal with is the data, and certainly the ground truth data, because we pair raw data with a ground truth data. So what should be done when the ground truth data are missing? So that's the main question that we have to face on. So we can obviously try to make simulation, data generation, data augmentation, produce some synthetic data on the computer itself, or We can use transfer learning. That means we use already a pre-trained model and that we only fine-tune with lace data, or use self-supervised techniques. Another way is to make active learning, so it's a little bit more technical, that one. So we rely also on something that already exists, and we just try to increase the accuracy of the model, or use different models to take the best of the two worlds. And there is other technique which is more difficult to control, the weak supervision on the semi-supervised systems. So I will go very fast on the denoising, because I think it's the topic of Joran just right after, but it's just show the most elementary image restoration that we have, and we can speak about the physics-driven and the data-driven. I call it web here for you. So again, before to start about denoising, we should know what is the noise on the image. So here I only consider the noise which is pixel independent. So that means if I take 2 pixels which is close, it's completely the noise is independent. So the noise on the top of the pixel is independent to the closest pixel. So it's because there is other kind of noise which is structural noise that we can maybe see in that case. So we do not consider that structural noise as a noise for microscopy. So pixel independence. After, you should know what kind of distribution of the noise you have in your image. In microscopy, we have a lot of shot noise, photon shot noise, that gives this kind of effect where we count the number of photons. But we have also Gaussian noise, we can have uniform noise, and most often we have a mixture of different level of different distribution of noise. Obviously, if you know perfectly the noise that you have in your image and the distribution of the noise, it's pretty easy to design the exact denoiser. But most often you don't know exactly what happens in your systems. So during starting in the 70s, people have tried to develop many kind of algorithms using classical method or using deep learning method. Here you see the number of papers that came only about denoising. So if you try to think about denoising, so most of you probably, when you think about denoising, you think about Gaussian filter or maybe Median filter. Median filter is a nonlinear filter, because these tools exist in every software. So that's the first thing that you can do. But it's a completely naive approach, because you have to set up something and you do not consider any kind of model of the noise behind that. So people have developed the rule-based method. In that case, the idea is to smooth, to blur the image, but preserving the edge. So there is a very famous one, which is anisotropic diffusion, which is full of parameters to tune based on the result that you expect. And now, if you are speaking about the physics, if we're speaking about the physics-driven method, so that in that case, we try to denoise, but we inject prior on the solution. And there is generally 2 prior that we can use, is the sparsity prior or the self-similarity prior. I should say that one is very common in biology, because here we process by the image by patch. So that means if we have similarity between the patch or in the image, we can make a non-local mean of the patch to try to denoise the image. And that works very well in biology. And obviously, we have the data-driven method with the supervised learning or the self-supervised learnings. And nowadays, there is also the generative denoising. It's more, it's using the kind of, the model diffusion and that kind of things. But it's too early to speak, because, okay, we do not have really a well understanding of what happens in that case. So very fast on that topic, because I think Johan will explain. So we have the supervised method, and so we have the noise. We train a network with noisy image and ground truth images. Obviously, the question here is where we can find the ground truth image. That means noiseless image. So we can use simulation, or we can use higher illumination to produce good images. It's difficult to generate. And more interesting is the self-supervised method. There is the noise to void, which is very interesting, and the noise to noise, and noise to void. And I think Johan will speak more about that one. So now deconvolution. So I speak about deconvolution because, okay, first I know very well this topic, but also there is all the concepts of the image restoration in that case. So what is the deconvolution in microscopy? So first we are in 3D. So in that case, the goal is to reassign or to reattribute the out of focus light to the original point source. So we have a lot of out of focus due to the fact that the PSF has these shapes. So in the Z direction, you see that we have a very good light in the focal plane, but if we are far away from the focal plane, we create some kind of haze, we start to blur the image, and that create the autofocus that we can remove very well with the deconvolution if we know the shape of the PSF in the Z direction. So in the lateral plane, that create also this kind of airy pattern that blur the image. So the goal really is to put back the photons where they belong, and such a way that we do not lose any photons. So the deconvolution will reduce the autofocus, reduce the noise, increase contrast, increase a little bit the resolution, and also enhance detail in the small structure. So how we can do a 3D deconvolution microscopy? So there is a first approach, the physics-driven method. So in that case, we have to take in consideration this equation, where we try to minimize this cost with two terms, the data term. In the data term, we take into account the physical model, age here, and we also add a regularization term where we integrate prior on the solution, and we let turn an optimization program to find the X tilde here. So in that case, so using that strategy, we're able to deconvolve this very nice C. elegans embryo. There is 3 channels here. We can pass from that image to that image using this strategy. If you want to try this kind of things, we have developed a plugins of Fiji Image, which is called Deconvolution Lab, that have different methods to different regularization terms, total variation or other, and different way to deal with this data term. Here we have the least square expression, or we can use a maximum likelihood expression. So there is different way to integrate data term and regularization. So now if we are thinking about a data-driven method for deconvolution, so in that case, we forgot everything about physics. So we just take in consideration that we have to find the best way to go from Y to X tilde. So from ground truth, how to pass from raw data to ground truth. So we have to create a data set, so pair of images. Usually it's a lot of images which is required. So that means it's a pretty computationally intense problem because it's in 3D and we have a lot of images, and so that you can imagine that it takes days to train such a systems. People have done here. The other big issue is how to find again ground truth data. So here in that example, so I give you 2 examples how to generate ground truth data. We can use physically acquired data. In that case, people have acquired data, ground truth data, with the 20x objective, and they pair it with the 10x objective. So the pair is two. So they have to switch very fast because we have to image the same sample with 2 kind of magnification. When you train such a system, you are able to pass from that one, so the 10x, to that image, to the network output. In that other examples, so in that case, they generate the ground truth using super resolution fluctuation techniques. So it's a microscopy techniques to obtain super resolution. So, but you have to acquire more images in that case. And after you can pair a low res with a high resolution images. So again, you have a list of pair of images. You train your systems, and after you are able to pass from the low res to the high res image. So that's not the only way to do it. So the people are thinking about the data-driven in other way, which is more a little bit more smart and taking into account the image formation model in the training itself. So you do not forget the fact that we have an image formation that we know. So you can learn the edge. Here we have so the PSF. Here we have a very nice example where the people have tried to learn the PSF, but also the variation of the PSF in the field of view. So that's a very interesting setup. You see that it's a huge machinery to obtain that kind of things, but it works, and that's very interesting. You can learn also the hyperparameter, how to deal with the data term deregularization, or you can most of the people try to learn now the regularization terms. Here there is another example where people have also tried to learn a very famous algorithm of deconvolution, which is called Richardson and Lucy, and they just taking into account also the PSF in the setup of in the loops of in the iterative loop of the Richardson and Lucy, and they are able to deconvolve pretty well the image. So in that case, we need also ground truth, because we need at some point, but we need much less ground truth because we take into account we are constrained by the physical, the image formation model and the equation that we have here. So it's not completely free. So there is some kind of constraint, and that's the constraint that we know that the image was formed in that way. Few results here just to show that the things that we can have. So here we compare the super illumination microscopy, so that's our ground truth, and we pair with the wide field, which is easily obtained from the super illumination microscopy. So we have the input, we have our ground truth, which is very well defined. Certainly we see in the z-axis that in the structural illumination microscopy will remove completely the out of focus. So we have something which is with a very good resolution. If we apply a standard deconvolution, okay, that gives some kind of result, and people have tried to learn and to train deep learning, and we can obtain that kind of things. There is also other setting that we can use is typically to use also dictionary learning. So that works. In that case, we learn some kind of patches in the image, and we specifically learn where we have a good resolution in the lateral plane that after we can put in the z direction. So it's other kind of techniques. Okay. So I will move to some consideration about the AI restoration, so risk and challenge, model and data. Okay, in that case, when you want to design a deep learning system for image restoration, so you are faced to all this kind of question. That's maybe not completely, there is other kind of question, but okay, the first one is, do I need really deep learning for solving my problem? So here the community move very fast with the deep learning, but sometimes there is some kind of overuse of deep learning. So maybe that's introduce unnecessary complication. If you have a very very good model. So the model is very explicit, or typical of the image formation. You don't need to spend time to have a ground truth data and so on. If you know exactly your model, you will be able to design exactly the image restoration algorithm that you need to solving the problem. So here we need a lot of education. So in image analysis and deep learning, and maybe it's part of this of your project also. So such a way that we should identify the case where deep learning is useful and the case where it's not. So the other thing that the other question, so now you say, okay, I do not have an explicit model, I want to have a deep learning stuff. So maybe the first things that you should do is to see if other people have already done some kind of job that are very similar, or or train some kind of models. So there is something which is called model zoo. Usually there is some kind of places. Maybe there is also one for your community. Here I just highlight one where I'm working on. It's one of the zoo, which is called the Bioimage Model Zoo. So in that case, we want to put together the people that produce the model, so the model producer. So typically the people that have to deal with Python and all this kind of very difficult library. And after if these people have trained models, they can share on this model zoo. And the model consumer, so here we specifically want to use the tools that people use in biology, in bioimaging. So IC, Joy, Elastic, Fiji, and so on, or ImageJ. And the goal is that the people have just to use the model that are already exist. And we have developed these tools, which is called Deep ImageJ, which is able to run this kind of model inside ImageJ without any effort. For the user, it's very simple to use it. So it is a specific model zoo is supported now by this European project, in fact, Euro-BioImaging also. It's called AI for Life. And the goal is to have interoperability between all this software. So a model could be trained on a software and used to another software. And we have to deal with the standardization such a way that the model are all the same format can be used for different people in the community. Other question that you should have if you find you do not find your models, maybe you have to think about retrain the model. So in that case, we speak about the fine tuning. So the fine tuning is so if you take a model that already exists, but it's not exactly the one that you want, you can specify the model with your own data to avoid what we call the data set shift and to avoid low performance and hallucination. So that's what we call the fine tuning. So that's require obviously less data. And the next one, so that's the more philosophical question: can I trust my results? So you see, with the deep learning, some people are very confident, maybe overconfident on the result, and others could be skeptical on the result because it's only based on the data. Here, the only thing that you have to do probably is to have more validation and to be able to interpret the result that you obtain with the deep learning and with the model that you have done. So now I will speak about the data. So as it's mentioned here, you see with deep learning, the data is the code. And the data could have bug, as we have bug in the code previously. So now maybe that the main task for the scientific is to design training data sets. So that means good preparation, curation, annotation, validation, avoid the bias in the data, integrity of the data, and obviously at the end you should also open the data used for the training. That's very important to well done this training data set, because everything relies on the data. The machine learning is only as good as the training data that you put in. And there is many risks. The risk of the data set shift. So you train a model with data, but you apply on another kind of data which are not exactly the same. there is a risk of overfitting, the risk of underfitting if the model is not enough large. The risk of bias, very often in biology, we have very rare phenotype that we do not learn very much because they are very rare. And there is also the risk of imbalance distribution. So we ignore the minority, which is really bad. So designing good data set, good training data sets is the key now. So how you can design. So the first thing in microscopy that we can do is to learn from paired physical acquired data. In that case, we acquire data, source data and target data, so raw data and ground truth. So here we have another example where people have acquired data in low SNR with a low power illumination and with a high SNR with a high power illumination. And again, you pair it and you are able to pass from this raw data to let's say to CARE or to other SRSNet, which is a good network also here. So you are able to denoise, maybe to deconvolve also your image in that case. Obviously, it's pretty huge. You have usually to take a lot of images. That's the limitation that we can have, and that's not so obvious. Here, the people have tried to so match the confocal with one scan and the low quality, high quality with 64 scan. Another way to obtain the image is to learn from artificial degradation. That's a very smart way. So you take your raw images, you degrade your image, maybe one time or two times, and then you learn from that image, how to pass from that image to that image. And then you apply from the raw data, you can apply your model to obtain a prediction from that image to that image, or maybe from that image to that image, and so on. So that's a very nice setting. So learn from artificial degradation. If you have a good image formation model, that works very well. Another way a very smart way also is to learn from the concept itself. Here, there is a very nice application from the CARE software. Here, the good data are extracted from the lateral plane. You know, in the microscopy, in the lateral plane, we have usually a very good resolution. In the axial plane, we have bad resolution. So that's typically what we have here, and the bad resolution in the z-axis. And what we have done here, what the people have done, is to learn from the lateral plane. So take patches in the lateral plane, remove some slices, and then learn the degraded version with the good one to apply and to try to restore very well the z-axis. So that's another way, a very smart way to learn to find where is the good data in the settings. So there is also this risk, which is the structure dependency. Yeah, there is a nice figure in this paper where the people have learned. They explain that you can put a blurry image and you can train a network to obtain a very famous images. But if you put a cat, probably you will find a sort of cat with a cell with a nuclei inside, which is not very good. Here I have another example. That paper, Anapalm, it's a system to obtain super resolution. So they train a system to pass from that image to that image, only in tubulin, so sort of filaments. They train also this system to increase the resolution of that to obtain that images. So it's on nuclear pore complex. And after, so they have two models trained on different data. And after, what we can do, here we use Deep Imager to make this experiment. We just permute the two networks. So we apply a prediction of the neural network on the NPC. So on that image, we apply the NPC model. So we obtain that one. On that image, we apply the tubulin network, and we obtain, you see that the system tried to create some kind of filament from the nuclear pore complex, which is really, really bad. It's what we call a hallucination also. So to conclude, I just want to, it's also a map to see how we can compare the physics-driven approach with the data-driven approach. So if you have a physical model of your image formation, so an explicit one, so it's required if you want to design a physics-driven method. Obviously, if you do not know how the image is acquired, you can go to the data-driven approach. But the drawback of the data-driven approach is to find a way to have ground truth data in the supervised mode, or a smart way to acquire these images. Probably the advantage of the so now there is always a question. So you build a system, but you want to improve the systems. So how you can do? So if you are in the physics-driven approach, so you can really see each step, and you have a measurement of how good is your systems. You can analyze the error and maybe improve something in your algorithm. In the data-driven approach, if you want to improve something, because it's a black box, the only way is to add data. And sometimes you add data and you have to add again and again. It's probably could be an endless process. So I have seen people that always add data to improve their systems, and there is no way to control the quantity of data that you need to that it works well. In terms of computation, so the time computation. So here it's okay, medium time. It depends on the size of the data and so on. Here there is two phases. The training phases, which is very slow, could take hours or days, and you need a GPU or very good machine to do it. But the prediction is pretty fast because there is no training. It's a one-shot operation. It's not an iterative process. So now the more philosophical question again is the interpretability of the things. So here we have a very good, we have guarantees of the convergence. So we know what we minimize, and it's easy to interpret what we obtain as a result, because we know exactly the cost function that we try to minimize. Here, the interpretation is more complex because it's based on the data set, and we have to deal with a black box. So there is no guarantee of convergence. It's only the huge amount of the data set that gives the solution. And the generalization. So generalization is a strong claim of the AI until the point that you do not have a data set shift. Okay, last slide. Okay, open science. So that's for the conclusion. So obviously we work in research, and we have to do everything open. So specifically for the deep learning, we have to open the data, make the data accessible with all the metadata. Obviously, open the source, the open source. And it's also important to provide a tool in such a way that the people can really use this technology. It's exactly what we do with the bioimage model Zoo, or with Deep Imager, with this kind of tools. We give the opportunity to the end user to use this kind of technologies. We have also a responsibility in terms of society, environment, and so on, and certainly about the sustainability, and to certainly there is this question of when we train a network, obviously that's require a lot of energy. It's not only the energy of the power consumption, but it's also the life cycle of the equipment. So we have to think about the gray energy that we need, all this data center, all this data that we have to store somewhere. And at the end, it's also the education. So I mentioned that. So it's really important that the people that have to deal with this technology are well educated, in same time in image analysis, but also in artificial intelligence. So that's, and probably that's the goal of this kind of workshops. It's exactly in this mind. Okay, thank you very much.